Yeah, it's visible.
Thanks. And thanks for all the participants spending. I plan to spend 1 hour with our lecture session on a Saturday afternoon. So the idea here was to decode the software architecture that is there in automotive embedded system, and we'll also throw some light on what is the current trend today and where this whole world of automotive embedded system is taking a shift and moving towards. So let me start my session with a simple question that will actually open up the participants that how big this industry is. How many lines of code is there in a typical vehicle software? When I say typical vehicle software, that includes the software that is getting into a chassis ECU, body ECU, instrument cluster ECU, infotainment ECU, and powertrain ECUs. So putting together any rough guess that these many lines of code is typically driving all the ECUs in your vehicle. We all know, we came from industry, we all know that the number of lines of code is a metrics or is a serious productivity measure of any developer. So can anyone um, put your answer on the chat, so we'll see what is the interesting answers that we are getting. I'm repeating the question again. How many lines of code is there in a typical vehicle software? When I mean by the vehicle software, I'm meaning the vehicle embedded software that is residing in different ECUs such as chassis, body, instrument, infotainment, powertrain, and etc. Please feel free to post your answer in the chat. Yeah, I'm getting different answers. 50 to 100 million, thousands, 20 million, 100 million. Krishnamurti is telling more than 100 millions. Nafis is telling 100 million. Okay, nice to hear. Yeah, it's more than 100 million. It's more than 100 million because here is a comparison that shows a typical vehicle car software is somewhere more than that of a software. Excuse me. Let me put it in the full screen. So that is more than the typical software company making a OS as a product. You can compare that with Facebook backend code, Microsoft Visual Studio product, or cars, your Mac OS X. So the actual number of ECUs that is residing is also increasing as the feature grows, and the number of car software, sorry, the total lines of car software is also keep on growing. And by 2030, what we see? Somewhere we will see a level 5 autonomous car, which is completely electrified and completely autonomous. It will be running around 1 billion lines of code. So what does this mean? So this means the market for the whole automotive embedded system is very huge, and the share of embedded system on the total cost of vehicle is is tremendously increasing. So to see this, so this is again from a different um, statistica. Whatever that you see on the y-axis is the like share of the total cost of the vehicle. In the x-axis, as the year progress, it's time, excess time in years. So you could able to see somewhere around 2030, the share of embedded system on the total cost of vehicle would be almost 50%. So that's why a vehicle is no more seen as a complete mechanical system or a mechatronic system. Now we are talking about software defined vehicles. So which means your behavior of your entire vehicle is going to be handled, controlled by the software that is completely independent on the hardware, and which is undergoing or which has some advanced features, very sophisticated features, and running on a powerful SOCs. So this is the drift that we are seeing, and we are somewhere in the middle middle of the game, and we all were experiencing this change. So we have seen the today's architecture, which is the distributed electrical and electronic architecture, which means you have to read this in this way. You have to read this in this way, and the x-axis is as the software numbers are increasing or as the feature numbers are increasing. So today what we see is the distributed electrical electronic architecture. That means each small functionality will have a dedicated ECU. It might be an 8-bit, 16-bit, 32-bit ECU, and each of these ECUs are again interconnected with the help of communication protocols like CAN, LIN, FlexRay, Ethernet. So many communication protocols you have. Then, so we started doing this uh, as a modular in approach there, which leads to the actual functional integration. This is what we are telling us distributed electrical electronic architecture. But from this, we are moving towards a bit heavier domain centralized architecture. So where we will have central domain ECUs which are powered by high performance SOCs. So you will have a dedicated ECU made of SOC which takes care of the entire operation of that domain, and you will have other smaller ECUs that is it again doing some low level activity, and which is in turn controlled by the central domain ECUs. And there are gateways and communication mechanism that will exist between central and cross domain ECUs. So slowly this change of distributed E to domain centralized E, we are seeing a shift of microcontroller based systems becoming your microprocessor specific systems. Then the next level, we are going towards centralized architecture. So where the zone oriented vehicle computers would be interacting with the certain functionality that is hosted in the certain vehicle function that is hosted in the cloud. So here we will have a completely independent software layer that runs on a hypervisor, or that runs on a particular core, or that runs on the high performance SOC, and you have some DevOps mechanism from your cloud to do firmware over the air, firmware updates over the air, and people are talking these technology as software defined vehicle. And once the application becomes completely independent, many different options and apps would be available from the cloud to the user. And this is where the old technology is heading. So this shift between distributed architecture to centralized vehicle architecture will again open up
Hello,
several.
Jegan. Sorry to interrupt you. Your
Yeah,
voice
please.
is not audible properly.
Still, am I
Hello.
am I audible now? Is it okay?
Your voice is fine.
Mm.
Mr. Sandamurthy, I request you to like rejoin, check check the data in your end.
Is it
Yeah,
okay
voice
for
is
others?
clear. Yeah, voice is clear. I'm
It
able
is
to.
okay for others, sir.
Thank you.
Yes,
Yes,
sir.
yes.
Voice is clear.
Thank you. Thank you. Fine. So whomsoever is experiencing some issue in the audio quality, I'll slightly increase my amplitude. So you can check data from your end. If not, try rejoining. Yeah. So we were this shift in the distributed architecture
Yes,
to,
yes.
yeah.
No. Okay.
Now is it fine? Yeah. Thanks. So this shift in the distributed architecture to vehicle centralized architecture will open up enormous amount of different opportunity, and it really requires a different kind of cross skilling that's expected on or that's expected from everyone. Now let's look at other interesting metric, how the software complexity in the automotive world is increasing, and with respect to the and how it is impacting the challenges of the time to market. So this report is from McKinsey again. So Even the data that is presented here uh, might be coming from McKinsey, might have or might capturing a bigger trend. There would be here and there misses, but it's giving a clear trend. um, in the last decade, if you see, between 2000 to 2010, the complexity of the software that is getting into your automotive is relatively grown by 4 times, which means the kind of software that we have deployed in the automotive in the year 2010 has grown by 4 times. Uh, the more number of features, more number of customization, the more number of fine tuning. In 2010, we don't have these many. Are in 2010 we don't want to adhere to whatever the powertrain norms that we are adhering to today, and in 2010 we don't want to have many mandated safety features that we have today in most of the vehicles. In that way, the software complexity has grown uh, by 4 times. Whereas if you consider the productivity, in the last decade it has grown by, I would say, the from 1 to 1.5. So what do you mean by this productivity? The way that we work, the way that we automate, the way that we leverage our skills, the way that we create our turn out or mature out our workforce, all this impacts on the productivity. So in that way, the productivity has the increase in productivity, because we are also finding new tools, new ways to reduce the time to market. So that has been increased only from 1 to 1.5, whereas the problem that we attempt to solve has grown to an extreme complexity level. Now, let's assume in the coming decade, there is going to be a major shift in the landscape, but there is going to be a major shift in this whole architecture itself, where we end up having or where will be implementing this vehicle centralized architecture somewhere towards the end of this decade. So the complexity growth seems to be growing in the same trend exponentially. But again, the challenge with productivity is where we stuck in solving many standard problems. So India as a country, if you take it has enormous opportunity again on uh, infotainment, ADAS, body comfort, driving challenging, cloud IoT, base OS. You can name um, at least 2 3 big GCCs or tier 1 companies working on these technologies, and there are almost all big OEMs as their footprint in India. So in the global footprint, I would like to highlight whatever that you see here. uh, so almost that is year and year. So India as a company is leading or is doing a lot in the automotive software export process. By 2030, this all would be eating the or your embedded vehicle software will be eating the high gear. So with having said this, uh, my thought here was to give a small warm up before we start the actual topic and demonstrate or show some of the factual data which says how big the automotive software development market is. So you might be coming from a different embedded industry experience, or you might be actually venturing or entering into automotive, or you might be working on some project and now you want to learn AUTOSAR. So and I think that those are the participants. Now let's get into automotive embedded software architecture. So as a whole architecture, this is this for networking we have a standard ISO OSI layer standardization. Similarly, for automotive vehicle software architecture, you can refer this particular arrangement as a standard architecture, where you have your vehicle and that's mounted on sensors, actuators, power components, and that is in turn mounted on some ECU hardware. On top of that, you have your operating system. On top of that, you have your analytics, uh, or AI engine. On top of that, you have your applications. Then on top of that, you have your UI UX. Then further going towards connectivity and cloud. So this is the architecture which we are forcing, or which the whole industry wants to implement in the near future. And how is the project happening in the real world? It's combination of um, system engineering with agile. So at a high level, at system engineering level, everybody follows a vSpice based, or sorry, A-Spice based process, and they have to implement the functional safety. And so typically this goes in this V cycle form. Excuse me. So a vehicle architecture will give the overall requirement. From that, a domain requirement is taken, and the requirement for that particular control unit is resolved. Then it's broken down further into component level software features and implemented over an agile cycle. The software uh, development for this component level system is actually happening in agile way, whereas the full process, if you see, it happens still in the conventional V development cycle. So it again depends on industry to industry and project to project. So this is one approach where we see both agile system engineering with ESPICE is going hand in hand. And before like understanding what is AUTOSAR, let's take one system as an example, uh, uh, where you have your infotainment system. This infotainment system is responsible for doing information and entertainment. It has radio, tuners, multimedia, phone connectivity, telematics, navigation, rear seat entertainment, voice recognition. So many features are there. And these applications, if I map, or if I broke that into an hardware architecture or software architecture, you will have an HMI system, then you will have an application and middleware, then you will have a operating system. Then on top of that, sorry, that operating system is running on a hardware layer. So basically the hardware layer gives you respective IO interface. It has device drivers, it has the protocol stack, and it has this protocol stack and drivers specific to the particular hardware unit. Then on top of this, you have specific to operating system, or the core OS. It might be an Android, um, or it might be an iOS based. You have seen different operating system that is now coming for automotive infotainment application. Then on top of that, you have specific applications for that hardware unit, like abstracting your navigation system and abstracting your entire networking system. Then on top of this, you have your HMI system, so which has the beautiful UI UX based things. AUTOSAR is also one such layered arrangement. The classic AUTOSAR follows a signal oriented architecture in which uh, the approach or the aim was to come from year to year. Yesterday, we made a custom software for the hardware that was selected. But today, the idea was to standardize certain things with AUTOSAR. So there are some hardware specific things in this. There are some um, what do you say? There are some middleware specific things again here. Then on top of that, you have your application software. So this goes like this. You have your um, standardized modules, and certain things are completely standardized, which is sold as a product, or what you refer to AUTOSAR stack is the result of the open standard that was available. Then using these standards, we are building communication stack, we are having OSEC operating system or AUTOSAR operating system, then we have diagnostics, CAN, FlexRay. Then on top of that, we have our application software. These application software are specific to customer needs. It can be an ACC, it can be a lane departure warning system, it can be a front light controlling system. So these things are built based on customer needs, whereas the middleware is built based on using the standards to meet the standards. So that's the idea. So now the whole vehicle software ecosystem itself is moving towards building a reusable assets. Here the idea of using standards or making certain things as standards is because we can able to reuse that component. And if the application software is also made by following the AUTOSAR standard, then it can be portable across ECU. So two major reasons. One is, how do we plug and play the application from one issue to other issue, which is the portability of the application software. And how do we reuse certain modules of our base software. So these are the two major objective what the classic AUTOSAR is trying to solve. So as I told you, the punchline, a tagline of AUTOSAR itself is cooperate on standards and compete on the implementation. So everybody, let's adhere with the standards that is defined by this AUTOSAR consortium, and you compete on implementing it. How efficiently you implement your BSW, or how new feature that you have introduced in your vehicle. So that determines the product value. So AUTOSAR stands for Automotive Open System Architecture. So AUTOSAR is an initiative that is supported by many global OEMs across the world. It's not only OEMs, tier one suppliers, tool providers, everyone were part of that consortium, being part of that consortium till now. And they are coming up with this, revising the standards over year and year again and again. And the objective of AUTOSAR is to specify an open standard architecture for the software interfaces for the most common ECU functionalities. So AUTOSAR will make it possible to reuse the application between ECUs, as I told you. So applications can be, in fact, application can be portable, and your base software can be reusable. So AUTOSAR improves the quality, scalability, software optimization, and seamless upgrades and updates. So these are the members that I was talking about, who are driving the AUTOSAR consortium. There are 10 core partners. So these companies are 10 core partners. It includes many OEMs and many popular tier ones. Then we have 51 premium partners, then 45 associates. Then there are some attendees. So the 51 premium partners includes general OEM, general tier one, standard software, tools, semiconductor industry, so on. So with the advent of classic AUTOSAR, what is the gain like everybody is achieving? Why everybody is entering and forming this consortium, and they are contributing? So there are some benefits, like for each one of them. Let's assume a OEM is entering into this consortium. So it can establish development distribution. It can compete on innovative functions. OEM can simplify software and system integration. They can reduce development cost by drastically reducing the development time. So for OEM, there is a option of using multiple vendor software, since everybody's adapted and started following the same standard. Whereas for a tier one, the biggest advantage a tier one or supplier is getting is he can reduce the number of version proliferation, which means if you don't want to maintain multiple software for multiple customer and that keep on revising the version. So he himself is building the platform specific software based on open standard. So he might focus on revisiting, changing the version of those things. Then reuse of software modules across OEM also improves business to a bigger scale, because it's the same software that they are going to reuse uh, as a different module across supplier. So then it increases the application development efficiency, because the base software is completely attempted to reuse. So supplier also can able to work on the application development, and they can think of inventing a new business model uh, as a supplier, because they can support, they can participate in development given their relationship with OEM, or they can in fact um, come up with selling these certain solutions as product. They can come up with selling only the stack. They can come up with demonstrating certain skill, acquire new business. So always there is a scope for inventing a new business model for a supplier. And talking about tool provider, so tool provider has a very big potential in the market, because he is converting or encashing the whole standard into a product, and he is selling that. So interface with the entire development process, he can able to supply tools over across the V cycle, then embedded tools into an overall development. Then somebody who is actually newly entering into market, he can enable any new business model like consulting, training, and so on. So there is a potential opportunity in the market, even because the AUTOSAR standardization. People will say if this getting standardized, uh, um, many would be reusing the same code, and many um, would be stopping or would be losing their conventional jobs. It's not like that. Companies like tier one were making money during the upstream. No, they are making money during the downstream. So it's like whether you make money with selling your services, tools, and offer services from integration, or whether you participate on complete development. So always there would be a significant business for anyone in the market, as with this new AUTOSAR also. See, these are the things your AUTOSAR is actually bringing onto the table. One is exchangeability between manufacturers application, then exchangeability between supplier solution, exchangeability between vehicle platforms. So all these exchangeability is possible, which means I can exchange the software between different applications. I can exchange software between the same software between different vehicle platforms. I can exchange software between different suppliers. So supplier A might be working on chassis, body comfort, multimedia. Supplier C is also working on body comfort, powertrain, multimedia. So as a OEM, you don't want to rely on one single vendor. And there is a provision, since everybody is following on this standard, there is a provision for exchangeability. So here is a comparison between legacy ECU and AUTOSAR ECU. So each function in the legacy ECU has had its own system and microcontroller, whereas in AUTOSAR ECU, we will not see a super loop based software architecture. It's purely OS driven with basic functions, interface, and softwares. And these are called as standard platforms or platform specific softwares or platform specific vehicle softwares. Then in that approach, in the legacy ECU, the number of ECUs are growing very fastly. Here, certain things are standardized, and people work more on standardizing the interface for all the basic software. There, the hardware and software are closely dependent. Here, the hardware and software are completely, I wouldn't say completely independent, they are independent to a greater extent. Then, software supply is vendor dependent. Here, the software modules are exchangeable and reusable. It's not completely vendor dependent. So, with this introduction, I have to move on the AUTOSAR layered architecture. So, I'll just pause for a while. If you have any questions, please feel free to put it in the chat. So, I'm just looking at um, the chat window. Now we are in the domain central architecture and moving phase of domain fusion architecture. Yes, yeah, Krishnamurthi's statement is right. Any questions? Please feel free to post it here. Yeah, Vishal, please feel free to post your question in the chat window so that I can take. Meanwhile, I can get some water. So please feel free to post your questions. Okay. So if we have no further questions, let's move on. This is how the AUTOSAR has come up with a layered architecture solution. We have hardware. On top of hardware, we have microcontroller abstraction layer. Then on top of this microcontroller abstraction layer, we have services layer and ECU abstraction layer. Then RTE and application layer. So there is a reason for making these sort of L and inverted L and these bifurcation. It's very clear because your application should not directly make a function call, or application layer software should not directly call this one. If someone is completely new to this layered arrangement, let me give a small um, way to visualize it. Assume that these are .c .h files stored in different directories and folders. Each entity is consists of several number of .c .h implementation, and this application layer is also finally coming from .c .h, or coming as a .c .h, and this would be calling a function that is defined in the below layer, and this would be in turn calling a function that is defined in either of the below layers. So that is why it is called as a layered architecture or layered arrangement. There is a function call from one file to other file. It is because, or it is resulting you the layer change, or it is so that is what we are calling as layer. Finally, when you convert this into a full-fledged software, there is nothing called as a layer. This whole layer arrangement is for our understanding and for our reusability purpose. So this is on the AUTOSAR architecture side, or AUTOSAR layered arrangement. If you drill down, we will try to understand more about the functionality of MCAL, the functionality of services layer, functionality of ECU abstraction layer, complex driver. Then there are standard interfaces, standardized interfaces. There are AUTOSAR standardized interfaces. There are AUTOSAR interfaces. We can talk a lot about interfaces also. If you see the AUTOSAR application software, which is called as AUTOSAR ASW, this AUTOSAR ASW doesn't follow a layered architecture uh, specific style. It purely follows something called as a component style arrangement, which means if you have worked with any ARTA specific software development, you will see there will be a multiple task arrangements. So the similar way we have the application layer containing of component style arrangement, like each of the component is representing a application software, or each of the component is called as a single ASW or SWC. So that SWC is further interacting with your RTE through AUTOSAR interfaces. These interfaces can be a sender receiver interface, can be a client server interface, or can be a mode switch interface. So each of the interface will have a different unique mechanisms for exchanging data and services. Now let's get into layer by layer. We'll talk about MCAL. If you change your hardware, the major layer that gets impacted is only your MCAL. And if at all you have some piece of code on the complex driver, you have to think how to port the complex driver on the new hardware. Then you have to make certain modification on the AUTOSAR OS part of the services layer. So these are the piece of code that gets majorly impacted. But uh, at a large extent, if you are changing hardware, if you change your MCAL layer, you don't want to change anything else. So that was the idea, because your MCAL is fully dependent on hardware, or MCAL, you can say MCAL abstracts the higher layer from the hardware. So in the AUTOSAR MCAL layer, these are the peripherals that we have inside a microcontroller: watchdog timer, GPT, MCU, flash, EEPROM, then HSM, hardware security module, SPI, CANLIN. So for each of them, MCAL will have IO drivers, wireless COM drivers, communication drivers, crypto drivers, memory drivers, microcontroller drivers. You'll have all these things. So this is how typically it works. There will be a parameter definition, uh, which is actually done at a AUTOSAR config tool. This AUTOSAR config tool will help you to create a ECU description file in the form of ARXML, as well as in turn this tools will have inherent code generators, which helps you to generate the configurated files, which will have the extension of cfg.c and cfg.h. So these configuration files again has to be compiled with the software stack or stack that you are buying, which contains all the static code. Now let's take a CAN stack as an example. So this CAN stack will be residing or will be cutting across various layers. So one layer can be um, your ECU abstraction, one layer can be on your services layer, and one component can be on your MCAL layer. Then we have excuse me. Then uh, we have an application that uses your CAN stack through RT. So this complete application to hardware flow is called as one AUTOSAR stack. One such AUTOSAR stack that we are now going to see is CAN stack. So the purple color items, what you see here, all these are part of services layer. Then this particular green color layer that you see is the hardware abstraction layer or ECU abstraction layer. So this pink color layer that you see is your MCAL, microcontroller abstraction layer. Now we'll see on top of this you have your RTE, runtime environment. Then we have the application layer. We'll take CAN stack as an example, and we will try to understand what is the default functionality of each of these modules and why it is used. Then we will understand what you'll be finding in the communication hardware abstraction, and then what you will have at the MCAL. Let's go module by module. So above RTE, if RTE is sending a signal, that would be received by the COM stack. So COM stack are the AUTOSAR COM module. It's called as COM module. If it is COM stack, that indicates this entire stack. Communication stack is called as COM stack. Here, what we refer by COM is the COM module. So this COM module transfers the signal from the RTE. So before COM module, or the data is called as signal. Whatsoever data that comes from your RTE is called as signal. And from here, we will start calling it as PDU. So the COM module is responsible for packing the signal to a PDU at a transmitter level, and at a receiver level it unpacks the PDU and provides the signal level access to the application. So these are the two core major functionality of COM. In the COM module, we will configure some of the generic parameters that are associated with the COM. Let's say if you want to filter out any signal, we'll filter the signal configuration, and we can configure cycle time, repetition time. So all this general configuration with respect to communication is configured at the COM module. The next module is EDU router. So now we have signal converted into PDU. So COM module or neither RTE doesn't know the data or the signal that it is sending is going to go out of the ECU through the CAN controller, which means the application, neither COM nor RTE, doesn't know that this data is going to, or this is a CAN data, this is going to take the CAN hardware or CAN controller channel, and this is going to be placed in the external CAN network. So that information will not be there. So that classification is first done at the PDUR level, which is called as PDU router. So this PDU router maintains the routing table exclusively for each of the PDU. Let's consider this. This module is responsible for routing the PDU to the respective bus. When we say respective bus, the bus are specific interface modules. The bus can be Ethernet, bus can be LIN, CAN, or FlexRay. So PDU takes a respective, PDU router takes the respective PDU and it sends it to the bus specific interface module. Then in CAN, it routes to CAN IF and CAN TP and DCM. Depending on your CAN configuration, it might send to CAN TP, or it might send to CAN interface, or it might send to diagnostic communication module, which is DCM. And the above PDR module, all the PDUs are, so just above your PDUR module, all the PDU stands for protocol data unit. Whatever protocol data unit that is above this PDUR is completely independent of your network, whereas that is coming out of your PDUR, now that is dependent on your, or that will have, that no, it would be routed to which specific protocol. Then we have CAN IF module. This CAN IF module is there in the ECU abstraction layer, and this is responsible for services like transmit request, transmit confirmation, then your controller mode rejections, and then majorly let's say you have this CAN controller connected as an external interface. The driver for that external interface will be part of the CAN IF module. And in this mode, particularly the PDU is called as interactive PDU at this level. So that interactive PDU is linked to the corresponding hardware object, irrespective whether the CAN ID is 29 bits or 11 bits. So that can be configured as a separate parameter. So PDUs, this whole stack, or the data, this whole stack is called as signal PDU. So it is called as IPDU, NPDU, LPDU, depending on which layer that it is. Now, as I told you, there are three possibilities by your PDU router. It can either transmit the data to CAN interface, or CAN TP, or to DEM. So DEM is the adjacent module that's part of diagnostic stack that is not shown in this COM stack. Excuse me. So basically, this CAN TP module offers segmentation service. So the segmentation services means when you have payload more than 8 bytes, when we are sending a large amount of data, or the payload is more than 8 bytes, the transmission and reception message control flow, assembling, reassembling the segmented message at the receiver and transmitter is done by the CAN TP. So whenever that we have flexi data rate CAN, whenever we want to pack more amount of CAN data, during that time, only during that time, this CAN TP module is configured. Then we have CAN SM module and CAN NM module. CAN SM stands for CAN State Manager. CAN NM stands for CAN Network Manager. So this CAN SM module, this module is responsible, or this module controls the entire state mission of your CAN network. And it is based on other state missions of the BSW layer like ECUM, BSWM, and COMM. So there are other state managers also residing in your BSW network. One is called as ECU manager, other one is ECU mode manager, other one is BSW mode manager, other one is communication mode manager. Depending on these mode managers, your CAN SM is responsible for selecting the state of the mission. Then you have CAN NM. So this CAN network management is hardware independent protocol, but the main purpose of this is to transition between normal operation, bus sleep mode, and bus wake, and network based NM frame reception and transmission. So your CAN network management module is responsible for transitioning the bus mode itself. Then we have the CAN transceiver driver. The CAN transceiver driver includes, or this CAN transceiver driver is part of ECU abstraction layer. The primary functionality of the CAN transceiver driver includes controlling the external CAN transceiver hardware, and it is also would be participating in the wake up and sleep process of the CAN. Then finally we have our CAN driver. CAN driver indicates the lowest part of the overall layer. It performs the actual hardware access. Here you can configure the CAN buffers. Then it talks directly to the CAN hardware banks. And each of the PDUs has to be tied with the CAN controller object at this level. So this is about the complete stack includes MCAL. Now let's talk a bit about, I hope now you come to know what is there in the service layer, what is there in the abstraction layer, what is there in MCAL layer, specific to a protocol stack. So it is along with the COM, PDU, CAN, NM, CAN SM, the service layer also as AUTOSAR OS, which is responsible for resource allocation, for scheduling, where we does all these activities. Now, finally about RT. So RT is the most complex piece of layer because it needs to know the functionality might be straightforward. It is getting the data from the above layers and passing it to the below layers, or getting the data from below layers passing to the above layers using AUTOSAR interfaces. But the challenge of implementing RTE is you need to know about the entire piece that that is built together as a software. Let's say, for example, in this RTE, you need to know, or on top of the RTE, tier 1 service software component is running, supplier software component is running, OEM software component is also running. Then different basic software suppliers are there. So there BSW1 supplier component is running, BSW2 supplier component is running, some OEM specific software component is running in the name of complex drivers. Now we need to have the ARXML of all BSW OS, then on the software components, then only we will have the complete detail that is required by the tool to generate RTE. So RTE acts like a Java virtual machine on top of, or which actually abstracts all the low level functionalities, memory mappings, variables. So this RTE also have some basic libraries, environmental variables, which we would be using on the runtime. Mostly this RTE is also in classic AUTOSAR. It is entirely written with C only. So, but if you don't have ARXML for all these details, you cannot able to complete, or you cannot able to completely generate the RTE. So this is the various phase how RTE is implemented. So RTE implementation happens in two phases. One is called as RTE generation and RTE contract phase. So as a first step, we'll have collection of all available software component ARXML. Then we'll take the extract of ECU specific information. Then we'll upload that into the AUTOSAR ECU configurator editors. Then we'll generate RTE.c, RTE.h. At this RTE.c, RTE.h is compiled, um, and then we will have compiled RTE, which is actually implemented along with BSW, your software component implementation, and that is how your final ECU executable is created. On a simple term, if I want to tell, you need to have the details of the entire ARXML, be it application ARXML as well as the base software ARXML. Now, let's talk about the AUTOSAR application development approaches. So here, so far what we have seen is what is there in the AUTOSAR RTE, what is there in the below layers. This whole below layers are a layered arrangement as we see earlier, and they are configurable. So it's like they are, when we say they are configurable, the static code is already available and sold in the market, and we are taking it, and it comes up with a configurator tool, and we configure, we generate the code, and that is compiled with the static environment, and that's how the final executable is created. Whereas the application layer can be hand coded or can be developed using an MBD approach. So there are two possibilities for AUTOSAR application development. One can be a top-down approach, and other can be a bottom-up approach. So in a typical top-down approach, what we have is we have to export the software component description file. Then this exported software component description file is taken into tool like Simulink. So here we start from the ARXML file. That's called as top-down approach. So we will have a schema, or we will have some AUTOSAR authoring tool that generates the software description file, and we import the uh, AUTOSAR authoring file, sorry, AUTOSAR ARXML that comes from AUTOSAR authoring tool into Simulink environment. We design its internal behavior, we simulate, test, generate code. So this is the typical flow that we take, and we call this as a top-down approach. Whereas in the bottom-up approach, we will create a Simulink model. Then that Simulink model, certain AUTOSAR configuration properties are set. Then we simulate, test, then we generate code, then finally we merge. In both the cases, we are using models to generate the code. But this model is preferred when we are migrating our old legacy models to AUTOSAR model. But this model is widely popular because before I build the model, I will export the software component description file from the authoring tool. So that is the idea. That's the difference between top-down approach and bottom-up approach. So in the top-down approach, we'll analyze the ARXML, import ARXML, develop model, perform model verification, do code generation. So in the code generation also, you will generate the source code for the software component that you implemented, as well as you will generate the updated software component ARXML. Whereas in the top-down, bottom-up approach, there is no ARXML file existing at all. Only the model is existing. So it will take the developed model, will verify, will map, do Simulink AUTOSAR mapping. So Simulink AUTOSAR mapping is all about creating which variable follows which input, outputs, which interface mechanisms. Then we generate the code. While the code is generated, the software component ARXML is also created. Then we will use this ARXML, or we will merge this ARXML further on after analyzing. Hope this is about how your top-down approach happens, how your bottom-up approach happens. And this is about the RT generation. This is about the application software development. So with this, I came to a conclusion of um, a generic introduction to classic AUTOSAR. So if you are an classic AUTOSAR engineer, you can either be a BSW integrator, or you can be an architect who is creating all this ARXML, or you can be working at the MBD doing bottom-up or top-down approach. So to understand the larger picture of AUTOSAR, um, Skill-Lync is coming up with a solution along with Electrobit, and we are starting a new program. Maybe Venkateshwaran will give you gist of that program, and I'll start talking more about that program. Venkateshwaran, over to you, Venkatesh.
Thank you, Jegan. I'll just open up the brochure. I'll just share my screen once. There are a couple of questions there. Do you want to take up
Yeah.
that?
We will take up those questions.
Yeah.
I'm not seeing that in my chat. Sorry.
It is in the Q&A window. Press the.
Okay. Okay. Yes, the participants would be getting the copy of those webinar also. Sir, is this session layer is in help? AUTOSAR, I didn't get that question, Prithviraj. Can you reiterate what you are trying to ask? Prithviraj is asking a question. Sir, is session layer is is help in AUTOSAR? I didn't get that question. Sorry. But yeah, Venkateshwar, you please proceed. Share
Please
the
scroll down. There are a couple more questions.
okay. According to the layer diagram, application layer cannot directly interact with microcontroller abstraction. Yes, the understanding is right, Siddharth. The application layer should not call or as per AUTOSAR standard. If it is calling the AUTOSAR microcontroller abstraction layer, then you cannot able to port the AUTOSAR software component from one ECU to other ECU, since it starts having a direct dependency on the MCAL. So how particular, okay, there are other questions. Prithviraj is asking how that particular application layer help in AUTOSAR. So the application layer, as I told you, it's your actual functionality implementation itself is there in the application layer only. Which means if your ECU is going to do adaptive cruise control functionality, that algorithm, that logic itself is there inside the application layer only. So that is the mandatory thing to have, or that is the mandatory software piece for which we build the whole system, or for which we build the whole ECU. So development model means it is using MATLAB or any. Sarvan Kumar is asking, mostly if it is development model, it is MATLAB and Simulink only. There are other tools available in the market like ASCII from ETAS that also will do this similar task. So how much knowledge of MBD is required to learn AUTOSAR? It should not be viewed like that. Let's say, for example, if you are working completely as an application engineer, you should focus learning everything from the MATLAB MBD perspective. But if your focus is more towards becoming an BSW developer, your focus should be more on the below part, at the below layers. Can you please give some more details about ARXML? As I understand, it is used to generate the RTE file. So what else we need to generate, or what else we need? See, how ARXML file communicate with application layer and BSW? Aishwarya, that's a nice question. ARXML file just contains the schema of your software component. That too, if it's application layer, it will contain what is the internal behavior of your software, what are the interfaces, what are ports, what are those names, what are the details of those things. So that is what an ARXML file will have. ARXML file will not have anything that is required for your application to communicate with BSW. ARXML file is the, if you save your static configurations, the what you have done for RTE, or if you are using any authoring tool to create your application ARXML, only that schema is created in that authoring tool. No code or nothing to do with communication of your application and BSW. It's just like an Excel sheet containing some information. Here the file format is XML. That's the difference. If we are changing hardware, it affects on MCAL services, MCAL service layers, and CDD. Yes, you are right. If you are changing Pradit Patil, you are right. If you are changing hardware, if because we don't know what is there inside the CDD, there might be some hardware specific things that's directly having there, so there is an impact. Any coding knowledge is required, absolutely, Saravana Kumar. Coding knowledge is, without having programming prerequisite, one cannot able to enter into AUTOSAR. If at all you are entering, you can learn this configuration, you can understand certain things, you can uh, do this parameter configuration, but um, at the end, the integration is all about reading the code that was generated or reading the code that was actually existing. So you will not be completely spending your energy effort in writing codes, but as an integration engineer, you will be reading a lot of codes. So a very, very clear, solid understanding of programming is required.